Okay, Walkers. Today we're going to get to elegant simplicity. Pascal's triangle and a binomial theorem. Warm up. Evaluate each expression. Number 1, 5 factorial is 5 times 4 times 3 times 2 times 1. So let's go ahead and do that calculation. So 5 times 4 times 3 times 2 times 1 is 120. Okay. 2 factorial times 3 factorial is 2 times 1 times 3 times 2 times 1, which we can do this without. Desmos 2 times 3 is 6 times 2 is 12 times 1 is 12. Okay. Now, 5 factorial divided by 3 factorial is 5 times 4 times 3 times 2 times 1, which we already did that calculation, which is 120. 3 times 2 is 1 is 6. 120 divided by 6 is 20. Let's go and take a look at the next page. Before that, almost forgot. You know how to expand binomials in the form of a plus b to the n using the distributive property. How can you expand binomials when n is a large number and distributive property would be difficult to use? Now let's look at the next page. Getting started. In a blaze of glory, there is an interesting pattern of numbers that make up what is referred to as Pascal's triangle. The first 6 rows of Pascal's triangle are shown where n equals 0 represents the first row, n equals 1 represents the second row. Analyze a pattern in Pascal's triangle. Describe all the patterns you see in Pascal's triangle. All the numbers are positive. The numbers are symmetric about a vertical line through the apex of the triangle. Complete the rows for n equals 6 and n equals 7 in the diagram of Pascal's triangle. Describe the pattern you used. Let's take a look at the next page. Activity 2.1. Explore patterns in Pascal's triangle. Mathematicians have discovered countless interesting patterns and relationships with Pascal's triangle, despite the fact that Pascal's triangle has been around for centuries. Even before the time of mathematicians, Blaise Pascal, for whom it's named, new patterns are still being discovered. Because the triangle is infinite, there may yet be patterns that have not been explored. Brianna loves hockey. In fact, Brianna is so obsessed with hockey that she drew hockey sticks around the numbers in Pascal's triangle. Lo and behold, we found a pattern. Her work is shown. Describe the pattern shown by the numbers inside the hockey sticks that Brianna drew. The sum of the numbers along the longer part of the stick is equal to the number at the end of the shorter part of the stick. Sketch one more hockey stick that includes the numbers that have the same pattern described. Okay, you can see that 1 plus 1 plus 1 plus 1 plus 1 equals 5. All right, let's take a look at the next page. Drew and Natasha analyzed Pascal's triangle and each described a pattern. Drew, the sum of the number in each row is equal to 2 to the n, where n equals 0 represents the first row. Let's take a look at Drew's first. So for n equals 0, 1. 2 to the 0 is 1. For n equals 1, 1 plus 1 is 2. 2 to the 1 is 2. For n equals 3, 1 plus 3 plus 3 plus 1 is 8. 2 to the third is 8. For n equals 4, 1 plus 4 plus 6 plus 4 plus 1 is equal to 16. 2 to the 4 equals 16. For n equals 5, 1 plus 5 plus 10 plus 10 plus 5 plus 1 is 32. 2 to the 5th is 32. So that's Drew's. All right, let's take a look at Latasha. Latasha, if I alternate the signs of the numbers in any row after the first row and then add them together, their sum is 0. For n equals 1, negative 1 plus 1 is 0. For n equals 2, negative 1 plus 2 minus 1 is 0. For n equals 3, negative 1 plus 3 minus 3 plus 1 equals 0. For n equals 4, negative 1 plus 4 minus 6 plus 4 minus 1 equals 0. For n equals 5, negative 1 plus 5 minus 10 plus 10 minus 5 plus 1 is 0. All right? both are correct. Either verify or disprove each student, which we have verified. Okay, 3. Consider the numbers along the dashed lines. Write the sequence for the sum of the numbers along each dashed line. They are 1, 1, 2, 3, 5, and 8. Explain how the sum of the numbers along the dashed lines in the Pascal triangle can be linked to a well-known sequence of numbers. The sum of the numbers along the dashed lines are the Fibonacci numbers. Each of the Fibonacci numbers is the sum of the previous two. All right, let's take a look at the next page. All right, the teacher explained 4a, 4b, 4c, and 4d on the next page. The patterns shown in Pascal's triangles have many uses. You may have used Pascal's triangles to calculate probabilities. Let's explore how you can use Pascal's triangle to raise a binomial to a positive number. The student will work 4e. And we're going to go and mark off this section and that section. All right, let's take a look at the next page. 4. Multiply to expand each binomial. Write your final answer so that the powers of a are in descending order. Anything raised to the 0 power is equal to 1. Anything raised to the 1 power is itself, so this is a plus b. Now, a plus b squared is equivalent to a plus b times a plus b. So we need a 4. A times a is a squared. A times b is plus ab. B times a is plus ab. B times b is plus b squared, which is simplifies to be a squared plus 2ab plus b squared. Okay, a plus b cubed is a plus b times a plus b times a plus b. So let's go ahead and FOIL. And this might get long, so let's start all the way to the end of the paper. A times a is a squared. A times b is plus ab. B times a is plus ab. B times b is plus b squared times a plus b. Now we can combine terms here and here. So then that becomes a squared plus 2ab plus b squared times a plus b. So now let's FOIL. A squared times a is a cubed. A squared times b is plus a squared b. 2ab times a is plus 2a squared b. 2ab times b is plus 2ab squared. B squared times a is plus a squared. Plus a b squared, and then b squared times b is plus b cubed. So we have a cubed. Let's see if we have any combined terms. That becomes plus 3a squared b and then plus 3ab squared plus b cubed. All right. And then the student works 4e. All right, go ahead and start working on that and have a wonderful Wildcat day.